Okay, trig integrals. I've already done a few examples in the last video, in the first one. What we're going to do now is we're going to back up and make explicit something which I may have already said. I'm not exactly sure, but if I have said it, repetition is pedagogically advantageous. Never a bad thing to repeat it. But let's go ahead and make it explicit, perhaps again. When I'm looking at these trig integrals, what's going on here and what gives me the confidence to actually start fiddling with all of these in the way that I have been is the curious fact, it may appear curious, that sine and cosine are not just related in Pythagorean relationship, they're also related in derivative relationship right here. Okay. We also happen to know that our trig relationships of tangent and secant are also related both in Pythagorean, okay, and in derivative. The relationship, with these two is a little bit different because the derivatives go from first degree to second degree. But there still is that relationship. Tangent and secant related here, tangent and secant related here, tangent and secant related here. Okay. We also know that when we're dealing with cotangent and cosecant, we have that same kind of relationship. And cotangent x is negative cosecant squared x. So the only real difference between the second line here, between tangent and secant, and of course cotangent and cosecant, the main difference is the fact that cosecant and cotangent both have negative derivatives. So you have to fill around the negative. But this is what gives me confidence to do all the changing of form that I've done up to this point, okay? So from here, let's just go ahead and just march through a bunch of examples, and I'll sort of highlight certain things as we move through. Let's go ahead and do sine cubed x cosine squared x dx, okay? That's sine cubed and cosine squared. Sorry, that 3 is a little bit squinched. This one can actually only be done one way. Okay? And the reason is that sine is of an odd degree and cosine is of an even degree. So if I go off and change that cosine squared into 1 minus sine squared, there's going to be no cosines left over for the inevitable du that I'm going to need for the integration by substitution that's necessarily going to take place. But if I take the sine squared out of this sine cubed and change it to 1 minus cosine squared, then I have a sine x left over to be part of my du. Now, here's the thing. I don't need sine x. I actually need negative sine x. So if I want to put a negative right here, I can either put a negative out in front, or I can use that negative to flip the difference. I'm going to go ahead and flip the difference. Now, that means that I have the integral of cosine to the fourth x minus cosine squared x. And of course, this negative sine x dx is going to be my du for both terms. Now, I think we've gotten to the point where we're familiar enough with u substitution where we don't actually have to go through the process of splitting it up. Once I split it up into two separate integrals, this is going to be u to the fourth du, and this is going to be u squared du. So I know that I'm going to get 1/5 u to the fifth minus 1/3 u cubed plus c. And that is going to be my integral. Okay? Now that's easy enough. You know, so what we did is we looked at both of them and I said, okay, well, the odd one is going to give me my du, so I need to pull one of those out and then change the rest of them using my Pythagorean identity. What happens, however, if they're both even? Like, what if they're both squared? Well, if I change sine into 1 minus cosine squared, I don't have any more sines left. If I change cosine into 1 minus sine squared, I don't have any cosines left. So I'm in kind of a pickle right here, except for the fact that I happen to remember that sine x and cosine x both have power-reducing identities that I showed you in the last video, right? And we basically went from cosine 2 theta times 2 cosine squared theta minus 1. And I used that and just did a little bit of algebraic work and isolated the cosine squared. And it showed me that 1 plus cosine 2 theta over 2 is equivalent. And I made a similar move over here from the third form of that double angle identity for cosine to show you once you've isolated sine squared that it's 1 minus cosine 2 theta over 2. Okay. Well, let's use both of them, okay? And so I have 1 minus cosine 2x over 2, 1 plus cosine 2x over 2 dx. It's easy enough to go ahead and pull a 1/4 out in front and then FOIL those two. I mean, it is the difference of two squares, okay? Well, that should be easy enough. What I'm going to do from here is I'm just going to, obviously this is a cosine squared alone, I'm going to have to power reduce again, okay? And in preparation for that, I'm going to go ahead and turn 1 into 2 minus 2. And I remember that cosine winds up being the sum, right? So it winds up being 1 plus cosine 4x over 2 dx. Well, in that case, we can actually pull out another 1/2. And basically, once that happens, this is going to be 2 minus. Now remember, that numerator is functional parentheses, so I'm going to need to distribute that here, and I'm going to get 1 minus cosine 4x dx. Well, once I do split that up, and I'm going to go and split it up just so you can see it a little bit better, I recognize the fact that, and I'm turning it into 1 over 32 because I'm anticipating the fact that I'm going to need a 4 dx for my u sub here. That's going to be 1/8 x minus 1/32 sine 4x plus c. Okay, and we had two integrals that looked awfully similar, one being sine cubed cosine squared, one being sine squared cosine squared, but they wound up giving me very different answers because of the nature of it. Now, you got to remember that basically once these are both squared, that makes this a very different function in terms of symmetry than we have here, right? So cosine is even, so cosine squared is going to be even. Sine is odd, so sine cubed is going to be odd. That's an odd function right there. And that right there, though, is an even function. And as a result, we're going to have very different ways in which those integrals actually work out. If you want to, pull out your calculator and actually see the difference in the graphs, and I tell you what, we have a second, so why don't we just go ahead and do that. Okay, sine x, and let's do the first one, that's cubed, cosine x squared, and then we have sine, actually I should have done it the other way because then I could have just done y1 times sine, squared. And let's go ahead and change the window. Oh, that's actually 0 to, let's go negative pi to pi. And let's go negative 2 to 2. It's not going to go that far, but okay, here is the sine cubed cosine squared. Okay, and we see it's odd, right? And here comes the sine squared cosine squared. And we see that it's even. I mean, over here, these look like very, very similar functions, okay? Here, however, we can see the difference, okay? And that's going to be what results in radically different looking integrals, okay? Now, let's go ahead and move on to another example. How about x cosine squared x dx? Well, we've already talked about how some of these wind up being a combination of techniques, and it should be very apparent right here, right now, that this is definitely going to be parts. Okay, and you know that because these are two different classes of functions. That's trig, that's polynomial. Okay, but even now, I want to designate x as my u, because I want it to go away once I start doing my parts, which means that needs to be my dv. I can't do that as my dv yet, okay? So why don't we go ahead and change that using, of course, the power reducing. Okay, and so let's pull that 1/2 out in front, and we're going to get x plus x cosine 2x dx. And that gives me a very easy integral on the first round. And the second one, it's not really all that bad. It's just one round of parts, right? Okay, well, let's go ahead, and for this one right here, I know that my u is x, and therefore my du is dx. My dv is cosine 2x dx, and therefore my v is going to be 1/2 sine 2x. Okay, and we'll box that just because I don't like it to merge in with the rest of the notation. And so let's go ahead and integrate that first one. That's going to be 1/4 x squared. Now let's go ahead and put brackets around, because remember, when you do parts, you wind up getting two terms. That's a difference. 1/2 x sine 2x minus 1/2 sine 2x dx. Okay, well, already I know that I'm going to need to put a 2 in here, so this is going to have to change to 1/4. Okay, well, let's go ahead and do the next row right here. Obviously, those first two terms just come along for the ride. They've already been done, right? I simply have to worry about what goes on here. Well, when I integrate sine 2x, it becomes negative cosine. So that changes this sign right here, and I get cosine 2x plus c. That right there is my integral. So I wound up using power reducing and parts. Okay. Well, let's do one more example before we call this one, or maybe one or two, depending on how quickly we get through this next one. How about tangent cubed x dx? Well, we saw secant cubed, and it wound up being parts, so this makes us a little bit nervous. But here's the thing. Is this parts? And the answer is actually no. Because, I mean, the first thing you should do is just sort of play with it anyway, right? And this winds up being tangent times secant squared x minus 1. That winds up being tangent x secant squared x dx minus the integral of tangent x dx. This right here is u sub, that's u du. So I wind up getting 1/2 tangent squared x. Well, that first term is easy enough. What is this? Well, there's two ways that you can do this, because remember that the integral of tangent x is natural log of secant. Well, it's natural log of secant because you had to change tangent into sine over cosine, and then include a negative, and that negative wound up turning cosine into secant by properties of logarithms after you were done. So this can either be by formula, just go ahead and plug it in, or it's plus natural log of cosine x plus c. Either way, it really doesn't matter. Okay? Okay, well, I'll tell you what. Let's go ahead and do one more, since actually we do have a second here. We're right at about 15 minutes, but we'll definitely get this one in underneath the 20-minute mark. And so we have secant to the 6th x dx. Well, this actually should be really, really straightforward. It certainly doesn't have the pitfalls that secant cubed had, right? It's even in terms of its degree. So we can actually split that up into secant squared squared times secant squared x dx. And this in the brackets becomes my du when I inevitably change that secant squared into its tangent equivalent. And once that becomes tangent squared x plus 1, and I FOIL it, it wound up being tangent to the 4th x plus 2 tangent squared x plus 1 times secant squared x dx. And like I've said before, we don't actually have to split it up into separate integrals to know what would happen once I do. Tangent to the 4th is u to the 4th du. That winds up being 1/5 u to the 5th. Same thing with tangent squared. It becomes 1/3 tangent cubed, but there's already a 2 there, so I have to combine it with that, and it becomes 2/3 tangent cubed x. And then my last integral, if I were to actually split this up, is just secant squared. Well, secant squared very easily gets integrated or anti-differentiated into tangent, and then we just have to tack on the plus c. Okay. We'll go ahead and get to, we'll actually do a couple in the next video that are definite integrals. We'll get to a couple of cotangent and cosecant ones as well. And then after that, I think that'll be 3 videos on trig integrals. I think that's just about what we need. I'll move on from there and do a few videos on decomp. The first one will probably be just reminding you the rules of decomposition into partial fractions. It should bring memories back very, very quickly, since we covered that extensively over the last 2 years. And then in successive videos, we'll go ahead and look at how that factors into integration as a technique. Okay. Any questions on anything that I did in this particular video, go ahead and shoot me an email. Bye.